Hey everyone, in this lecture, we're going to be talking about streams and floods. And some of the material we've already talked about in previous lectures, like the depositional environments and things like that, but it's always good to go over a little bit more specific things about rivers, streams, and flooding. So in this lecture, we're going to learn what streams and drainage networks are, how they form and evolve, how to describe stream flow and erosion, and how streams transport and deposit sediment, how the character of streams changes from headwaters to mouth. Those are some terms that we're going to define. How erosional and depositional landscapes form by streams and how those evolve over time as well. And the nature of flooding and the steps that we can take to protect ourselves against flooding events, and the environment issues that pertain to streams. We're going to talk about watersheds and water and things like that. Okay, so a stream is any body of running water that flows in a channel. And a channel is an elongated depression or trough. And some of the things that, some other words associated with that are stream bank, which is the edge of a channel, the stream bed, which is the floor of the channel, and the reach is the defined length of the channel. The headwaters is the source, which is typically upstream, and water flows from upstream to downstream. So you start at the headwater and then you end at the mouth, which is the direction in which the water flows. It's like the outlet, basically, of a system. And when we have too much water in our stream system, that's when we have a flood. This is when the supply of water entering a stream exceeds the channel's capacity. So you have water that goes over those stream bank, it goes over those edges. So when we, how do streams form? Well, when we have water that comes off of melting snow or from rain, and even sometimes groundwater springs, it accumulates and it puddles. And when it exceeds that, then it flows. So if we just have a lake or something, those are the bounds of that body of water. But if we also have a slope change, this is when we have water that moves from one direction to the other. And this is where we get drainage networks, and this is where we get the formation of streams. So in the image down below here, we have an example of where we have snow melt, which adds water to the system, or if we have a bunch of rain, it first forms a puddle, and then as there's an excess of surface water, this is where we have the headwater here on the left and the mouth over here on the right. We also have the contribution of the water table, which then feeds into this stream system. And we're going to have a lecture more about groundwater and the water table and all of that soon. So there's a few different types of drainage networks. We have dendritic, rectangular, trellis, radial, and parallel. So let's look at all those individually. A dendritic drainage network looks like this here on the right, and that's when a river flows over a uniform substrate and they develop a dendritic network that looks like branches of a tree, basically. That's how it got this name. And so this is where we have a fairly uniform surface, and it just looks like they just kind of branch off into these different systems here. And that's different than a rectangular system where there's natural fractures or joints in the substrate. So this is where channels follow pre-existing fractures and the streams join each other at right angles. And this is where we get a rectangular network. A trellis network is when a network develops across a landscape of parallel valleys and ridges. So we can see that these are the parallel ridge, and here's a parallel valley. And they join a trunk stream that cuts across the ridges. And then it looks kind of like a garden trellis. If you had any vines, you see that they kind of grow up one, and then the vines kind of go off on their own direction, and that's what this is. This resembles. And next is a radial network. This is where networks form on the surface of a cone-shaped mountain or perhaps a volcano, and it flows outward from the peak, like the spokes of a wheel. So here's an example with a volcano, or this could be a mountaintop or something, and we have a radial drainage network off the sides of this cone. And then we have parallel network, and this is where we have steep uniform slope. And we have these streams that are parallel to each other and they develop simultaneously. So if we have a huge input of snowmelt or rain, they follow the ridges, for example, of the topography. And this is where water flows in a parallel direction to each other. And so when we look at, we've talked a little bit about slope stability in a previous lecture, when we talk about land mass movement. And so it's somewhat important to talk about slope stability here because we have all these different types of stream networks, and a stream is dependent on a change in the slope. Otherwise, we would just have pools of water or lakes and things like that. So you have to have a change in slope or a huge change of influx of water in order for water to move from one direction to the other. And so when we talk about land mass and we have an influx of water, and that can change the slope stability when we have changes of mass change in mass due to water in a gravel or the topsoil, that changes the land's ability to stay put, and so it wants to slide. And so when we talk about what water does to the surface of the earth, slope stability is a big part of that. So we have drainage basins and divides. This is where how we define different parts of land. And sometimes it's separated from topography. Sometimes it's separated from often rivers and things like that. So if you've ever wondered how certain highways across the United States or maybe state lines are divided, it's sometimes dependent on watersheds. And a watershed is a collection of water from a drainage network over a broad region. And a drainage divide is a highland or ridge that separates one watershed from another. So sometimes these drainage divides and watersheds are how some counties get their shape or some states get their shape. So I'm going to hit pause here, and what I want you to do is just do a little research and think about what watershed do you live in. Maybe that's the school or maybe where you live, and try to find some information about what watershed you belong to.
A little later.
Okay, well, if you live near Moorpark area in Ventura County, actually this covers quite a bit of Ventura County, you might belong to the Callenguas Creek watershed. And here's a map of that. So here's part of Ventura County. This is part of southern Ventura County here. And if you were to research the watershed, we would see that the watershed has quite a bit of beneficial use. And so this map divides out how some of this water is used. And so green, we see that that's open space. What are some of the other colors that we see here? A lot of this pinkish color, which means it's residential. So a lot of you probably live here in this area. And so a lot of the watershed is used for residential use. We have some mixed urban, we have some commercial as well. So all these different, and some industry and industrial. So you see the little pockets of red here, those are for industrial use of the watershed. So watersheds, again, are divided into municipalities or cities, and they have the jurisdiction over them. And it's important for future use and sustainability that the owners of the watershed protect the water. Otherwise, you have an issue where you have people using too many resources, or there's no way to sustainably have enough water for things like residential areas or for agriculture. And so if we look at all the uses within this watershed, we have everything from wildlife habitat to agriculture supply, groundwater, warm water habitat, shellfish harvesting. There's a lot of different uses of water just within this one watershed in Ventura County. Okay, so let's talk about the different types of streams. So first is a permanent stream. And a permanent stream contains flowing water all year long. And so where the bed of stream lies below the water table, this is typical in more like temperate or tropical climates, or where there's a constant flow of water. And so this is where we have the water table feeding into a stream system constantly. An example of this would be the Mississippi River, where it's always a river and has always been a river. And the difference of that between ephemeral streams is that an ephemeral stream contains flowing water only part of the year or not consistently. And that's because the water table can fluctuate, or the water table might be lower than the channel itself. And so some survive during the duration of like a wet season and dry up during a dry season. So a wet season would be like where we have a lot of snow melt or something like that, or there are a lot of rain. And then in the summer months when it's quite dry, there's no water in the stream. And streams whose watershed lie entirely within arid regions like deserts tend to be ephemeral. A lot of our stream systems here in Southern California are ephemeral because you might be able to notice them if you go hiking a lot or something and you say, oh, I remember that this stream had water in it a few months ago and now it's dried up. So here's an example, a picture of that, where we have in the dry time, you can see the banks of this. And then during maybe a wet part of the season after a big rainstorm or something, it's just totally full. So when we talk about stream discharge and turbulence, here are some vocabulary words that we might use to describe how the stream water moves. So discharge is the volume of water that passes through a cross-section of a stream in a given time. A stream's average discharge reflects the size of its drainage basin and the climate. So you would expect a lot more drainage if you have a lot more input, and the discharge of that is proportional to how big it is. So a really, really large river is going to have a lot more discharge. And the turbulence is the twisting or swirling motion of the fluid. And these produce things like eddies, which is where water curves and flows upstream or circles in place. So here's an example of a model of where you have little barriers in between the flow. That's what these little panels are. And so if we see how the water flows, you can create some eddies here, and you see how the turbulent the water can be with these different zones. So this helps us understand what water turbulence is and how this might affect things like the erosional processes that take place around a river. So here's an example of some stream erosion. So this is where we have, so gravity is basically the energy that makes the running water move from, a high topography to a low topography. And with it, it tends to erode away sediment. So we have a few different ways that streams do this. We have scouring, which is where running water can remove loose fragments of sediment. We have full-on breaking and lifting, which is where there's a big flow of water that can break off huge chunks or solid rock off of the floor or a wall. We have abrasion, which is where clean water has very little erosive effect, but sediment-laden water acts like sandpaper. So as a slurry gets loaded with sediment, it can grind away the floors of a channel or a wall. And then we have dissolution, which is where running water dissolves soluble minerals and it carries the minerals away in solution. So streams transport sediment, and there's a lot of different ways that we can understand how sediment is moved. So the total volume of sediment carried by a stream is called a sediment load, and there's these different components. First is a dissolved load, next is suspended load, and the third is bed load. So first is dissolved load. And dissolved load is where we have running water that dissolves soluble minerals in the sediment or rock that it flows over. And groundwater seeping into a stream brings dissolved minerals with it. So this is done. The dissolved load is really not necessarily something that you can really see because it has to do with the dissolving of minerals. And this exists here in these dissolved ions, this part of the diagram, where we have a little blown up view of what that looks like. Then we have suspended load, and this consists of tiny solid grains, usually the size of a silt or clay, that swirl along the water without settling on the floor of the channel. And so this is where we see, if you've ever stomped through a river or a stream and you kick the bottom of the floor and it creates like a little dust cloud in the water, that would be something that creates a little bit of that suspended load, and this has all those clay particles. And the next is a bed load. And the bed load is the large particles like the pebbles and the sand that you see, and these bounce or roll along the stream floor. And bed load movement commonly involves saltation. And saltation is where we have different grains that bounce along it within the direction of the flow within a zone that extend from upward to downward in a stream bed. And each grain in this zone follows a trajectory through the water and then back down to the bed. So as it bounces, that it might get kicked up and then slowly move down with the flow. So saltation is where you have these sediments, they hit the floor, they kind of bounce up, get suspended, and then slowly move back down. And so that's how we get this tumbling effect. So if you've ever gone to a river and you see how perfectly smooth some of these river rocks are, that's because they've gone through a lot of this saltation process. This is where the bed load is then kicked up, pushed, and tumbled along with the flow of the water. And here's a YouTube video that shows that. So we just talked about how sediments can be suspended and ultimately they can be deposited. So sediments transported by a stream are called a fluvial deposit. And this should be a review based on the depositional environment lecture a few weeks ago. And this is where gravel in a stream bed of a mountain stream, there's this picture here shows that where we have large clasts that are carried during floods, and then smaller clasts are carried further down. And this is where we get deposition of different types of gravel and things like that in stream bed. And when we have different types of streams, we get different types of deposition. So here's a stream here. And when we have where we have these elongated mounds of sediment, these are called bars. And when a stream is moving very broad and curvy like this, that's called a meandering stream. And water flows along the inner edge of the meander and creates a crescent shape like this point bar. So again, this is where sediment is accumulated along a point bar. And basically you have flow that erodes away on the outer side of this and then deposits on the inner side. And you might think about this if you're driving in a car, you feel more of the turn as you turn more sharply than the other. And so this is kind of the idea, is that you have erosion here on the outside and then deposition on the inside. During floods, a stream may overtop the banks of its channel, which is called a floodplain. And this represents here a floodplain, which is like a broad, flat area that borders a stream. So here's our stream that comes out, and this whole area represents the entire floodplain. And a delta is where a stream empties at its mouth into a body of water and the water flows and a wedge of sediment accumulates. So here's an example of some deltas here. This is where we have sediment accumulating in between these little flows of water. Let me move my face so we can see this whole image. We also have an example here where we have valleys and canyons. So the shape of the canyon or valley depends on not only the resistance of the walls of erosion, but also the velocity, the rate of the mass movement, and sometimes those sediments that are carried along with this water. So we have an example here of a slot canyon where we have water that erodes over time, and as it encounters a softer sediment below, this is where we get a shape that looks like a slot, basically, where it's vertical, and then it kind of opens and bows out beneath it because we have a change of resistance within the different soil types or rock types. Here we have a V-shaped valley, and this is where water erodes into a valley shape, and over time it just creates this V. So it starts off like this, and as water flows, it continues to cut down into the subsurface layers, and this is where we get a V-shaped valley. And in areas where we have a kind of combination of these two, where we have different layers of soft and hard sediment or rock, they erode at different rates. And so this is where we might see something like a stair step, where we have the softer sediments getting more eroded than the harder sediments. And so it's not quite as uniform as a V shape. Instead, it's more like a stair step. Here's an example of a braided stream. And a braided stream is where streams carry this abundant sediment during floods, but they can't carry the sediment during normal flow. So during normal flow, the sediment settles out and chokes the channel. And as a consequence, the stream divides into all these different strands, and they weave back and forth, and they create a bunch of these elongated bars. These are more sandy and gravelly. And so we see braided stream systems where over time they kind of like lay on top of each other. And so this whole area is totally riddled with braided streams that have occurred over during flooding events, where one instance it'll flow in this direction, and then another flooding event would cause the stream to go more in this direction. And so they end up being like stacked, and you have a stack of braided streams. Here's an example of an alluvial fan. Again, this should be a review. This is where we have an ephemeral stream that emerges from a mountain or canyon like this, and then it opens up into a channel floor. And as water flows, it drops most of the sedimentary load. Usually here at the mouth is where we have sand and gravel and cobbles. And then further out on the edges of the fan is where we have finer sediments like clays and smaller particulates. So this is where we have a huge deposition of mass, and then it falls out into a fan shape. Again, here's another example of a meandering stream, and there's all these other things that can happen with a meandering stream. So this is where the stream follows the curve of least resistance, basically, and over time that could change. So the stream might go back and forth, and then the next event, because it curved out one stream over here, but then topography changed, or a flooding, there's more input to a water, so it changes its direction and then cuts off where the previous stream was. So an example of that is called an oxbow lake, where we have a meandering stream that once went all around this lake and back down, but then over time it just was like, I'm going to make a shortcut, and cuts this off, and that's called an oxbow lake. And sometimes this oxbow still contains water, sometimes it doesn't. Here we see, due to aerial photography, we can see where there's abandoned meanders. And so at one point, this meandering stream may have gone all the way up here and cut through here and maybe came back down, but then over time chose a different path. But we can still see where that river cut through the sediment or cut through vegetation. And here, this is where we can see a buildup of a lot of those point bars. And so this is where the river takes a sharp turn and deposits a lot of sand here and continues on. So this is where we have a change in velocity of where the stream prefers to turn. So here's another diagram of that oxbow lake. Again, we have erosion on one side and deposition. So erosion on the outside, deposition on the inside. And eventually, over time, the river's like, nah, that's too hard. I don't want to do that anymore, and just kind of cuts it off. And this is where we see that oxbow lake. Sometimes it remains with water and sometimes it doesn't. Again, here's another example of a floodplain. And so here we have a meandering stream that covers a portion of this, and the edges of the entire area is called the floodplain. And it's because during a flooding event, the water would, or during normal circumstances, it would follow this meandering stream. But during a flooding event, all bets are off. The stream could take whatever path it wants within this floodplain. And so some other words here that you might see throughout the presentation, or I might reference them later, is, again, we have those point bars. This is the bar of deposition. Sometimes this is called a natural levee, which is where it's built up on the side of this. And we have a lot of, in this cross section, you can see where we have the stream was once there, and then gravel was deposited on top of it. So sometimes when we see a cross section, we see the layering of all these different streams and all these different meanders over time. Okay, so here's an example of a levee. So this is where a low ridge that's created as water starts to spread beyond the channel during a flood. And so when we have a levee, it helps slow down that flow, and so that sediment settles along that edge of that channel. Here, this mossy area, that's considered a levee. And sometimes we create, so this is a natural levee, but sometimes we make levees because we want to try to contain the floodplain or contain a stream. So here's an example of a time lapse of a stream. So what happens when the stream exceeds the sides of the channel? Well, that's when flooding occurs. And this is when the volume of water flowing down a stream exceeds that volume of the channel and spills out over the normal bounds of the channel, and it spreads sometimes over that floodplain. And this is when water enters the watershed faster than can be evaporated or absorbed, and occurs when we have a heavy downpour or an unnatural amount of water input into the system. This can already happen when maybe the water's already, or sorry, when the ground is already saturated and there's no more room to absorb waterfall or snow melt. Or sometimes we get flooding when there's a dam break or a sudden release from a reservoir or something like that. And we have two different types of floods. We have seasonal and we have flash floods. So I'm going to go over these and then show you some videos of floods. So a seasonal flood is one that occurs during the annual wet season. This normally is associated with tropical regions during like monsoon rains, or in temperate regions when there's typical snowmelt in the spring. Those would be examples of seasonal flood where they kind of happen every year, versus a flash flood, which is where an event rises so fast that you can't really escape the path of the water. The path of the water may be unknown because there's so much water that you just don't know where it's going to go. And this is usually done when there's an intense rainfall or like a dam collapse. And the video here that I'm going to show you, I chose it because this is near where I grew up. And this was in 2013 in Manitou Springs, Colorado. And it totally wiped out the highway. And people are like getting out of their cars because they don't know what to do during this flash flood. And it happened so suddenly that people were on the road, and there was a huge rainstorm, and people like pulled off on the side of the road, and then this huge flooding system occurred, and it was like sunny and blue skies not too long after. So this is an event that happened very quickly and very destructive and can be quite dangerous. So let's look at some of these YouTube videos about floods.
Over the past 100 years, no other natural disaster in the U.S. has caused more death and destruction than floods. They can happen any place, any day, any time. And they will likely only get worse. As people cluster around coastal regions and floodplains, our growing population will confront the awesome power of water. For thousands of years, farmers have depended on seasonal floods. The waters irrigated their crops and fertilized their lands. Today, excess water is channeled into reservoirs and power hydroelectric dams. But when water levels rise suddenly, far more than the ground can absorb, a flood occurs. Flash floods are a perfect example. Sudden storms unleash a torrential downpour. The runoff moves with surprising force. At a depth of 2 feet, the water can push aside a car. In fact, half of all deaths from flash floods involve vehicles. But floods occur in many other ways. Heavy rains and thawing snowfall can overwhelm rivers. Storm surges caused by hurricanes and tsunamis inundate the coastline. Landslides and mud flows can displace large volumes of water. Dams break, levees fail. In the Great Mississippi Flood of 1993, several of these factors came into play. Over 10,000 square miles of the Midwestern United States were overwhelmed with rain. In a cruel twist, the earthen dams known as levees along the upper Mississippi River forced the water to flow downstream faster and stronger. Communities further downriver were hit with the full brunt of the Mississippi. 2/3 of all the levees were breached. Though towns rallied to protect their lives and livelihoods, the damage was still immense. Over $10 billion in damages, 56,000 homes flooded or destroyed, and some 50 people were killed. At the start of this century, another powerful flood wreaked havoc, this one coming from the sea. The storm surges of Hurricane Katrina submerged 80% of the city of New Orleans. Over 1,800 people died in the floods. The damage has been estimated at over $80 billion. In some ways, the New Orleans disaster was unique. Much of the city lies below sea level, and despite years of warning, the city was woefully unprepared to handle a breach of the levees which kept it dry. But we are still vulnerable. Sea levels may rise. Coastlines could erode. Rain patterns might change. Snowpacks could melt. And then the waters would rush in.
Okay, so like I said, there's things that we can do to try to prevent some of these flooding events. And we often try this ourselves. We create these artificial levees. And this is like a concrete flood wall along the bank of a river to increase the channel volume. So these levees isolate the area of the floodplain. And so sometimes they're naturally occurred, these levees, but typically man-made structures are there to try to prevent some of these large flooding events. So there's a lot of levees that are built in the New Orleans area. And if you remember, Hurricane Katrina was quite devastating because some of these levees broke. They said, okay, well, we put up a levee here and this will protect the city of New Orleans. But then the hurricane came and had so much water that the levee broke. And that's what really flooded a lot of the city and surrounding area near the Gulf of Mexico. So here's an important part of the lecture. When you purchase a home, you would probably get a map that says, okay, you live in a flood hazard area. And so this is a map of known discharge during a flood. And knowing the shape of the river channel and the elevation of the river bordering the river tells you if you're in a flooding area. So if you live close to a river, you might very well be in a flood hazard area. And so sometimes you read on or hear on the news about the size of a flood or the reoccurrence and probability of a flood. So the recurrence or annual probability for a flood reflects the size of the flood. So sometimes you hear the word like, oh, this is a 100-year flood. That doesn't mean that it's only supposed to occur every 100 years. That means that it has a 1% probability of occurring. So again, another example is if it's a 2-year flood, that means it has a probability of 50% occurring. So when we have these really large flooding events and they say, oh my gosh, this is a 100-year flood, this is devastating. That means that it occurs 1% of the time. That amount of water into the system, the input of a flood, it is about a 1% probability chance, not that it occurs every 100 years. So there's a little bit of misunderstanding of what that term means. We can have a 100-year event occur 2 years in a row. That just means that the probability of the amount of water into the flood has really exceeded the statistical probability of normal conditions. And so we see a lot more flooding events as we have increase in global warming and increase in sea level rise and changing of our climate. Things are a little bit hotter, so there's more snow melt that's occurring earlier or different times of the year. And so all of those things change the flooding occurrence. So streams can serve as avenues for transportation and can be sources of food, irrigation, water, drinking water, and others. So here are some environmental issues that pertain to rivers when we talk about what it means to have a river nearby, or what issues might arise from floods and what types of things can impact it. So of course, if we have streams and floods nearby with developed cities, there's usually pollution that goes with that. If we want to try to control these streams, there's usually dam construction. Like I said, when we looked at what watershed you might be in, there's issues of perhaps overusing water, and therefore we get some other issues with overuse, like subsidence and the land collapsing and things like that. We have urbanization on streams, so we try to control the direction of a stream or the bounds of a stream, so that we can build more properties nearby. And of course, we have effects of agriculture. And so much of Ventura County relies on agriculture. So it's important that we understand that there's enough water for not only residents of the area, but also for agriculture. So here are some of the things that we talked about today. We talked about what streams and drainage networks are, how they form and evolve. We talked about describing stream flow and erosion and how streams transport and deposit sediment. We talked about the character of streams, how they change from headwater to mouth, so from upstream to downstream. We talked about how erosional and depositional landscapes formed by streams evolve over time. and the natural causes of flooding and what we can do to maybe prevent some issues of flooding, like building levees. And there's some issues pertaining to streams. And we'll go more into the environmental issues when we talk about groundwater. So that's it for this one. See you next time.